Welcome back for another deep dive. You send in the research and we dive in.
Exactly.
And today, we're going to be tackling something pretty big, huh? The Earth's climate system.
It's a big one.
Yeah, it's a massive topic, and I think it's going to be really fascinating to break down all the different pieces.
Yeah.
So we'll be looking at how energy from the sun, the atmosphere, all the different layers, how they work together, and even how the ground beneath our feet plays a role in shaping the climates we see around the world.
Right. And I think the listeners sent in some really interesting articles and visuals this time. So
Yeah.
should
Yeah.
be a good
Wait,
one.
I was really impressed with what they dug up. Like, there's so much to unpack here.
It's amazing how much there is to learn about climate, isn't it?
Oh, absolutely. And I think one of the things that makes it so fascinating is that it's all connected.
Yeah.
Everything from the tilt of the Earth to the strength of a jet stream, it all plays a role.
Totally.
And I think that's what we're going to try to do in this deep dive, connect those dots. So why is it always beach weather somewhere? Why do other places bundle up for half the year? What causes those dramatic shifts in temperature and weather?
Right.
I
Right.
think those are some of the questions we'll be exploring. But I think a good place to start would be with the foundation, the most basic piece of the puzzle, energy from the sun.
Absolutely.
It seems pretty obvious, right? I mean, the sun's up there, it's shining,
Yeah.
but it's amazing how much the sun influences everything on Earth.
It really is. It's like the engine of our planet's climate system.
Yeah.
Pretty much all the energy that powers weather patterns, the ocean currents, plant life, it all comes directly from the sun.
That's right. And it's not just like a steady stream of energy either, right?
Right.
It travels to us in waves, right?
Well,
I was looking back at some of the materials. I vaguely remember learning about that in high school science class or something.
oh, absolutely. Yeah. You're thinking of solar radiation. So those waves of energy, they travel through space, and then when they're absorbed by the Earth's surface, the atmosphere, even clouds, it causes those things to heat up.
Yeah, and we feel that every day when the sun warms our skin, that's solar radiation doing its thing.
Exactly.
Okay, so here's a question, and maybe this is a dumb question, but if the Earth is constantly absorbing this energy from the sun, wouldn't it just keep getting hotter and hotter and hotter?
That's a great question. And it's not dumb at all. That's where the concept of what's called the net radiation budget comes in. It's kind of like a giant accounting system for energy.
Okay, so like a balance sheet.
Exactly. It balances the incoming radiation from the sun with the outgoing radiation that the Earth emits back into space.
Okay, so I'm picturing like a giant scale trying to stay balanced. What happens if we add something to one side of the scale, without taking anything away from the other?
It gets unbalanced.
Exactly.
Right. So in the case of the Earth's energy budget, greenhouse gases are the things that tip the scale.
Mm-hmm.
They act like a blanket, right? They trap some of that outgoing heat radiation.
Ah, okay.
It prevents it from escaping back out into space.
So the greenhouse effect, it's actually a good thing, isn't it? In moderation.
It is.
It's what keeps the Earth at a livable temperature.
Exactly. Without the natural greenhouse effect, the average temperature on Earth would be about -18 degrees Celsius.
Oh, wow. That is cold.
Yeah, that's much colder than the average temperature in Antarctica.
All right, so we need greenhouse gases to survive, but the problem is that we're adding too many of them, right?
Exactly, yeah. Human activities, primarily burning fossil fuels for energy, have increased the amount of carbon dioxide in the atmosphere.
Right.
And this excess CO2, it traps more heat than usual, and that leads to, well, global warming.
And that warming effect sets off a chain reaction of changes to the climate, which is why we hear so much about climate change these days. So it's not just about the temperature going up, it's about the knock-on effects, right?
Yeah. Exactly.
Yeah.
Yeah. And to really understand how climate works, we need to look at the different spheres of the Earth. There are four main ones. The atmosphere, the lithosphere, which is the solid Earth,
Okay.
the hydrosphere, all the water,
Right.
and the biosphere,
Yeah.
all living things.
So a lot of moving parts. But for today's deep dive, are we focusing specifically on the atmosphere?
We are. The atmosphere is where a lot of the climate action happens.
Yeah.
And it's much more than just air. It has a fascinating structure made up of distinct layers.
Layers. Okay, tell me more about that.
Or imagine stacking different types of blankets on top of each other,
Yeah.
right? Each with a unique purpose. The layer closest to the Earth's surface, where we live, is called the troposphere.
Okay.
It's where most weather happens. And those jet streams we hear about, they're whipping around high above us in the troposphere.
So that's where all the drama unfolds, the troposphere.
It is.
What about the other layers?
Well, moving up, we encounter the stratosphere, which is home to the ozone layer, our shield,
Yeah.
against harmful UV radiation from the sun.
Essential.
Above that is the mesosphere, where meteors burn up as they enter the atmosphere, those shooting stars we see sometimes.
Oh, wow. It's amazing how much happens in the atmosphere that we just don't even think about.
Uh-huh.
It's just there.
It is.
Okay, and the final layer.
The final layer at the top is the thermosphere. And in the thermosphere, the temperatures actually increase with altitude. And this is where you see these stunning aurora borealis, the northern lights.
Incredible. So we've got these distinct layers, each playing a specific role. But what exactly is this air made of?
Well, the atmosphere is primarily made up of nitrogen and oxygen, the gases we need to breathe.
Right, of course.
But it also contains small amounts of other gases, including those greenhouse gases we were talking about earlier.
Mm-hmm.
And even those trace amounts can have a huge impact on our climate.
It's like a delicate recipe. You add a pinch of this, a dash of that, and it can change the whole outcome.
Exactly. That's a great way to put it. And now that we understand those key players, the energy from the sun, the greenhouse effect, the structure in the atmosphere and what it's made of,
Right.
we can start to explore how they all work together to create all the different climates we see across our planet.
All right. I am ready to dive into those climate zones. I want to know what makes a tropical paradise so consistently warm and why some places are just locked in an icy grip for half the year.
Let's do it.
Okay, so we've got this incredible atmosphere, all these layers.
Yeah.
It's trapping heat, regulating the Earth's temperature.
Right.
But how does that actually translate into the different climate zones we see around the world? Like, why are there tropics? Why is there an Arctic?
It all comes down to how much solar energy different parts of the Earth receive.
Okay.
Remember that net radiation budget we were talking
No,
about?
it's a balance sheet.
Well, it's not the same everywhere.
Right.
Some places are definitely getting a bigger slice of that solar energy pie.
Yeah, that makes sense.
And one of the biggest factors that determines how much energy a place gets is its latitude.
Okay.
How far north or south it is from the equator.
Right.
So think about it. At the equator, the sun's rays are hitting the Earth pretty much directly overhead.
Mm-hmm.
But as you move towards the poles, the angle of those rays becomes more and more slanted.
Okay, so a more direct hit, more energy, more heat. Slanted hit, less energy.
Exactly.
So how does that create those distinct climate zones then?
Well, let's start with the tropics.
Okay.
Those regions near the equator, they're like the VIPs of solar energy.
You get the best seats in the house.
They do. They receive the most direct sunlight, and they have what's called a net radiation surplus, meaning they're absorbing more energy than they're emitting back to space.
Makes sense.
That's why they have those consistently warm temperatures and lots of rainfall.
Okay. So the further you get from the equator, the less direct that sunlight, the cooler it's going to be.
Exactly. So as we move away from the tropics and head towards the poles, we enter the temperate zones. And here, the angle of the sun's rays changes throughout the year because the Earth is orbiting the sun.
Right.
And that creates those distinct seasons that we experience.
Summer, when the sun's high in the sky.
Yeah,
Winter, when it's lower.
exactly.
Makes sense.
And then, of course, you have those polar regions.
Way up north, way down south.
Yeah, they're on the opposite end of the spectrum from the tropics.
We're getting the leftovers.
They are, yeah. In the polar zones, the sun's rays hit the Earth at a really low angle.
Right.
And this results in a net radiation deficit.
Okay.
They're actually losing more energy to space than they're receiving from the sun.
So they're in the negative.
They are.
Wow.
That's why they have those consistently cold temperatures, often covered in ice and snow.
All right, so latitude. That plays a huge role in shaping these broad climate zones.
It does.
But I know it's not the only thing, right? What about all that water we were talking about?
The hydrosphere.
Yeah, the hydrosphere.
Yeah, the presence of large bodies of water, oceans, lakes. They can have a huge impact on the climate of nearby land.
I've always heard that coastal areas have more temperate climates.
Yes.
Is that because of the ocean?
Exactly. Water has this incredible ability to absorb and store heat.
Mm-hmm.
And it heats up and cools down much more slowly than land does.
Right.
So coastal regions, they experience milder temperatures
Okay.
than inland areas because that ocean is acting like a giant temperature regulator.
So it's like buffering the land from those extreme temperature swings.
Precisely. And, the source material we were looking at actually had a great example.
Oh, yeah.
It had a graph comparing the average daily temperatures in Victoria, which is a coastal city in Canada, and Calgary, an inland city.
Okay.
And you can see very clearly how much more moderate Victoria's temperatures are throughout the whole year.
Interesting. So if you want to avoid those scorching summers and freezing winters, head to the coast.
Yeah, exactly.
All right. So we've talked about latitude, the hydrosphere. What about wind? How does wind play into all of this?
Wind is the unsung hero of the climate system.
Okay.
Global wind patterns, they're like this giant conveyor belt constantly distributing heat all around the globe.
Okay, so how does that work?
Well, remember how we were talking about the uneven heating of the Earth's surface?
Yeah, some places get more sun, some get less.
Exactly. Well, those temperature differences create pressure differences in the atmosphere.
Okay.
And air always wants to move from areas of high pressure to areas of low pressure.
Right.
And that movement of air is what we call wind.
Okay, so warm air rises, cool air rushes in to replace it, and that's what creates wind.
Exactly.
Okay, that makes sense. But I also remember learning about something called the Coriolis effect.
Oh, yeah.
Does that have something to do with wind patterns, too?
It absolutely does.
Okay.
The Coriolis effect is a fascinating thing.
Yes.
It's caused by the Earth's rotation.
Yep.
So as the Earth is spinning, it causes moving objects like air masses to be deflected.
Okay.
In the northern hemisphere, they're deflected to the right. In the southern hemisphere, they're deflected to the left.
So the Earth spinning underneath the wind is actually changing its direction.
It is.
Yeah. Okay.
And because of this deflection, winds don't just flow in straight lines from high pressure to low pressure.
Right.
They curve, creating these large swirling patterns.
It's like the Earth is playing a game of cosmic billiards with the wind.
That's a great way to put it.
I like that.
And these swirling patterns, they help to redistribute heat from the tropics towards the poles.
Okay.
And that helps to moderate the global climate.
So it's all about balance.
It is.
All right. So we've got these global wind patterns. They're driven by temperature differences. They're influenced by the Earth's rotation.
Yeah.
It's an incredible system. But what about those jet streams we hear about all the time?
Oh, yeah.
Are they part of this global wind system?
They are. Jet streams are a key component of those global wind patterns.
Okay.
They're like high-speed rivers of wind flowing way up high in the troposphere.
Right, that layer closest to the Earth's surface.
Exactly.
Okay, so what makes them so fast? What powers those jet streams?
They form because of sharp temperature differences between large masses of air,
Okay.
particularly between the warm air of the tropics and the cold air of the polar regions.
So temperature gradients again. Always back to temperature.
It is, yeah. Think about it. When you have a big difference in temperature, you also have a big difference in air pressure.
Right.
And just like wind flows from high to low pressure at the surface, the same thing happens up in the atmosphere where those jet streams form.
Mm-hmm.
The bigger the temperature difference, the stronger that pressure gradient, and the faster those jet streams flow.
It's like those temperature differences create a kind of atmospheric slope, and the jet streams are just rushing downhill.
Yeah, I like that visualization.
And it works for me.
And these high-speed jet streams, they play a major role in steering weather systems around the globe. You know, they can transport warm air to colder regions and vice versa,
Right.
influencing temperatures, precipitation patterns all over the place.
So when we hear about like a big shift in the jet stream,
Yeah.
that can mean some pretty big changes in the weather.
Absolutely. Yeah. Shifts in jet stream patterns can cause all sorts of extreme weather events like heat waves, droughts, floods, even blizzards.
Wow.
And they also play a role in larger scale climate phenomena like El Nino and La Nina.
Right, which can affect weather patterns across the entire Pacific.
Exactly.
Wow, it's incredible how all these pieces of the climate puzzle just fit together. We've gone from the sun's energy to the greenhouse effect to layers of the atmosphere to swirling wind patterns and powerful jet streams. And to think it all comes down to basic physics and the Earth spinning.
It really is a testament to how complex and interconnected our planet's systems are. And it's a reminder that even small changes in one part of the system can have ripple effects across the entire planet.
So let's do a quick recap of what we've learned today about the climate system. It all starts with the sun's energy, which drives everything. Then we have the atmosphere, that layered blanket of gases that regulates the Earth's temperature through the greenhouse effect. And then those temperature differences across the globe create wind patterns and those powerful jet streams that we hear about all the time.
And we also explored how those factors, latitude, proximity to water, and wind patterns work together to create the distinct climate zones we see across the planet. From the steamy tropics to the frigid polar regions, each zone has its unique characteristics shaping the lives of all the plants and animals that live there.
And those climate zones aren't static, right? I mean, we're hearing more and more about how climate change is messing with these patterns. What are some of the potential consequences of that?
That's a really crucial point. As we humans keep altering the composition of the atmosphere, mainly by increasing those greenhouse gas concentrations, we're basically turning up the heat on the planet. And that can lead to all sorts of effects. Rising sea levels, more extreme weather events, shifts in where plants and animals can live, and even impacts on things like human health and agriculture.
So it's not just about the planet getting a bit warmer, it's about these interconnected systems getting thrown out of whack, which can have pretty serious consequences.
Exactly. And the impacts of climate change are going to vary depending on where you are in the world. Some regions might see a lot more heat waves and droughts, while others see increased rainfall and flooding. Coastal areas are especially vulnerable to sea level rise, and a lot of ecosystems are going to face some big challenges as temperatures and weather patterns shift.
That's a pretty sobering thought. But it's also a call to action, isn't it? What can we actually do with this knowledge to address these challenges?
Well, knowledge is power, and understanding the science behind climate change is the first step toward finding solutions. We need to move to cleaner sources of energy, reduce our reliance on fossil fuels, and find ways to adapt to the changes that are already happening.
It's a huge challenge, but I feel like it's one we can tackle if we work together. And I think the more we understand about how the Earth's climate system works, the better equipped we'll be to make informed decisions and create a more sustainable future.
I couldn't agree more. It's about understanding that we are all part of this interconnected system, and the choices we make have an impact. But it's also about hope and the power of human ingenuity to find solutions.
This has been a truly incredible deep dive into how the Earth's climate system works. It's clear there's still so much to learn and explore, but I think even understanding the basics empowers us to start making a difference.
Absolutely.
Well, to our listeners, a huge thank you for joining us on this journey of discovery. Keep those curious minds engaged, keep learning, and let's all do our part to create a brighter, more sustainable future for our planet.